the second lecture on power system analysis revision course. So in this lecture we will see the complete fault analysis. See, basically we have a four different types of faults: LG fault, LL fault, LLG fault and three-phase fault. Three-phase fault means triple L fault and triple LG fault. But one important thing here is, if the system is balanced before the fault, then the analysis of triple L and triple LG faults are same. But before the fault, if the system is unbalanced, then analysis of triple L and triple LG faults are different. That is the first thing you need to be very careful. And the second important thing is, the most severe fault on power system is nothing but three-phase fault. Now out of this three-phase fault, triple L or triple LG is most severe. Yes, triple LG fault is most severe if the system is unbalanced before the fault. Otherwise, triple L and triple LG faults are having what? Same severity. Correct or not? So if the question is given, which of the following fault is more severe, means the best option is triple LG fault if you have what? Two options. Clear? And the next important thing is the most occurrence fault. The most occurrence fault is LG fault. Okay, the most occurrence fault is LG fault and least occurrence fault is three-phase fault. Among the three-phase fault, triple LG fault is least occurrence fault. Okay, clear? But one important point is, LG fault is the most severe fault at generator terminal. At generator terminal, if there is a fault, LG fault is more severe compared to what? Three-phase fault. Okay, and one more important thing is, if the neutral of the generator is grounded with very high impedance, then LG fault is not severe. Three-phase fault is more severe. So remember this point. On power system, three-phase fault is more severe. At generator terminal, LG fault is more severe. If the question is given like this, if the neutral of the generator is grounded with very high impedance, then which of the following fault is more severe, means you need to go for what? Three-phase fault. And most occurrence fault is LG fault. Least occurrence fault is three-phase fault, and that to what? Triple LG fault. Okay. And analysis of triple L and triple LG faults are same. But if the system is unbalanced before the fault, analysis of triple L fault and triple LG faults are really different. Okay, clear? And the next important thing is, whatever may be the type of fault, we have to find out what is the pre-fault voltage. If you are able to calculate the pre-fault voltage, that's enough. If you are calculated the pre-fault voltage, then the next step is immediately we can calculate the fault current using simple formulas. But the question is how to calculate the pre-phase fault. 90% of the problems, the pre-fault loading condition is not given. Pre-fault loading condition is not given means what? The system is not loaded before the fault. That is a fundamental assumption. If he has mentioned the pre-fault loading condition, you have to accept it. If the pre-fault loading condition not given, then the system is not loaded before the fault. In that case, the pre-fault voltage is considered to be 1 per unit. Okay, clear? Suppose sometimes what he mention is, he will mention that before the fault, at fault location, the voltage is so and so value. If that is the case, the pre-fault voltage is whatever it is specified. Okay, clear? Sometimes he will mention the pre-fault voltage. Let's consider that also. Clear? So, and the very least cases, he will give the pre-fault loading condition. If the pre-fault loading condition is given, then you must calculate what is the pre-fault voltage at fault location using simple KCL and KVL equations. For example, if the question is given like this, there is a generator and there is a transformer, and after the transformer a load is connected. He will mention that the load is drawing some X megawatt of power at some Y power factor at a terminal voltage of Vg. Okay, that is the pre-fault loading condition is given. But he will mention that maybe the fault is happened at generator terminal. Calculate the fault current or fault current contributed by the generator. In that situation, first what you have to do is, before the fault, what is the voltage? Since here the fault is happened now, that's why before the fault, so since here the fault is happened, before the fault, what is the voltage here you need to calculate. How to calculate? Very simple. Let's draw the equivalent circuit of generator, transformer, and after that what? Load. Clear? This is before the fault, and the terminal voltage of the load is given to you. Okay, and this is a transformer reactance, this is a generator reactance. Now this is nothing but V pre-fault, and let's calculate the load current. Load current you can find out easily using V, T, X and Y. That means the voltage, power in megawatt and Y in power factor you can calculate, and you better to convert everything onto per unit first, later you calculate. Once you calculate that, then what is V pre-fault in this case? Very simple. So Vt plus xt times jxt times, better to say jxt times IL. Now this is the pre-fault voltage will be used for fault calculations. Okay, so that's why, sir, three ways. Number one, pre-fault loading condition is not given, pre-fault voltage is not specified, take it as 1 per unit as pre-fault voltage. Number two, intentionally to create a confusion, he will mention the pre-fault voltage. Let's accept it. Okay. Number three, pre-fault loading condition is given something like this, and you can calculate the pre-fault voltage using simple KVL equations. So these are the three things you need to understand first. But again I am saying 90% of the problems he will not mention the pre-fault loading condition. He will not mention the pre-fault voltage. So let's take the pre-fault voltage is 1 per unit. Because for every fault, the pre-fault voltage is very, very, very important here. Now we will see the LG fault analysis. See, the assumption is that the before the fault generator is not loaded, before the fault system is already balanced. Now, let's say there is a generator and its neutral is grounded through an impedance called Zn. And at the terminals of the generator, there is a LG fault. See, this is what the three-phase equivalents of the circuit of generator. So, by default, LG fault is assumed to be on A phase. Nothing wrong to say R phase. You may say ABC sequence or RYB sequence. Okay. So, there is a LG fault on A phase. If there is a fault on A phase means this is the fault current. Now, what is the fault current? Equal to IA. Now, IB and IC are 0 because before the fault, the generator is not at all loaded. So, IB 0 and what? IC 0. Now, since the fault is on A phase, what is the potential from here to here? That is called VA. That VA is 0. That I have shown here. And VB and VC is not equal to 0. Now, if you write the sequence current relation, I am not going into the derivation. So, remember this. Sequence current relation is that using this information we can find out the sequence current relation, that is IA0 equal to IA1 equal to IA2 equal to IA by 3. So, sequence voltage relation is that since VA equal to 0, VA means what? VA0 plus VA1 plus VA2, that is equal to 0. Now, what is the fault current? Fault current equal to IA. From here, IA equal to what? 3 times IA1, 3 times IA2, 3 times IA0, that I have written here. See, this is the expression for what? Fault current. Now, what is a neutral current? Let's see this neutral current, if you apply the KCL at this node, the incoming current equal to outgoing current. We know that IN equal to IA plus IB plus IC. So that's why neutral current is what? IA plus IB plus IC. Since IB and IC are 0, the neutral current is nothing but IA, that is nothing but fault current. Now what is that fault current? Just now we have written expression, so that I have written again here. So the neutral current is nothing but simply 3IA0, 3IA1 and 3IA2 for LG fault only. So there exists a neutral potential here. Since the current is in this direction, this side is plus and this side is minus, and the neutral potential is simply IN into Zn. So that's I written here, IN into Zn, where IN is nothing but what? Fault current. Okay, so that's why minus IF into Zn. Okay, now we can write the sequence networks. Okay, since IA1, IA2, IA0 are same, I can write this is a positive sequence network, negative sequence network and zero sequence networks of generator. These three are now connected in series. Then only currents are equal. And what is this potential from here to here? VA1. What is this? VA2. What is this? VA0. The idea is very simple here. VA0 plus VA1 plus VA2 are what? Equal to 0. Equal to 0 means you need to represent with short circuit. Now I can calculate IA1, IA2, IA0 from here. Since we have only one voltage, three impedances are in series. So that's why. So I can write the IA1 equal to IA2 equal to IA0. That is equal to simply V pre-fault by Z1 plus Z2 plus ZG0 plus 3 Zn. Clear? That is the positive, negative and zero sequence currents. Now we know that the fault current is 3 times the IA1 or 3 times IA2 and 3 times IA0. That's why the final expression for fault current is 3 times V pre-fault divided with Z1 plus Z2 plus ZG0 plus 3Zn. Now careful here, suppose if the neutral of the generator is solidly grounded, then this Zn is what? 0. If the neutral is what? Solidly grounded, something like this. And this Zn equal to, you need to substitute infinity if the neutral is what? Ungrounded. For ungrounded neutral, indirectly the fault current is 0. If you have only one generator, okay, if you have n number of generator, then what you can say, this may not be equal to 0. Why? Because maybe this generator neutral is not grounded. Maybe other generator neutrals are maybe grounded. No? If all the generator neutrals are ungrounded, so in that case you can say the fault current is 0 for if all the generators are operating in parallel. Okay. So anyway, so for a big power system, how to calculate the fault current means you need to calculate positive sequence diagram, negative sequence diagram and zero sequence diagram. You need to see what is the Thevenin's positive sequence impedance, Thevenin's negative sequence impedance and Thevenin's zero sequence impedance. So in that case, what I get, IA1 equal to IA2 equal to IA0, V pre-fault by Z Thevenin 1, Z Thevenin 2 and simply Z Thevenin naught. Okay. Clear? For a big power system. Suppose if the network is given like this, let's say we have a generator, transformer, transmission line. Okay. So maybe this is at bus 3. At bus 3 there is an LG fault. Okay. Maybe the generator neutral is ungrounded. Here delta star grounded. Something like that. Then you need to draw the positive sequence diagram for this. And Z Thevenin 1 you need to calculate. You need to draw the negative sequence diagram and Z Thevenin 2 looking into the fault terminal you need to calculate. And you need to draw the zero sequence diagram and Z Thevenin naught looking into the fault terminals you need to calculate. And after that, what is the fault current expression? Same. 3 times V pre-fault divided with what? Z Thevenin 1 plus Z Thevenin 2 plus what? Z Thevenin naught. In that case, there is no concept of 3 times the Zn because that Zn is already covered when you are calculating Thevenin's zero sequence impedance. Okay, so please notice that. Anyway, so this is the expression for fault current if it is a LG fault. So the very important thing is for LG fault, all the sequence networks are in series and also VA1 plus VA2 plus VA0 is equal to 0. That's why there exists a short circuit across this series combination. And after that we can simply calculate the fault current. Okay, clear? And the next thing is, suppose if ZF is not equal to 0. If ZF is not equal to 0 means what is VA, IA, IF into ZF? Why? Because if you look back, coming back here, if ZF is not equal to 0 means there exists a ZF here. Now in that case, what is VA, IF into ZF? No, correct or not? Here ZF equal to 0 earlier. Now ZF not equal to 0 means VA equal to IF into ZF. That means with fault impedance effect, what happens? VA equal to IF into ZF. What is the meaning of this? Only voltage relation got changed, but fault current is again what? IA, IB 0, IC 0. That's why the point is, due to fault impedance effect, sequence voltage relation will change, but sequence current relations will never change. So VA equal to IF into ZF. If that is the case, let's come back. If VA equal to IF into ZF means VA0 plus VA1 plus VA2 equal to 3 into IA0 into ZF. So IA0 if we take common 3 ZF. Okay. So VA1, this is VA1, this is VA2, this is VA0. Correct or not? And if we add VA1 plus VA2 plus VA0, that is equal to what? IA0 into 3 ZF. That is the equation we realized using this circuit. So that means 3 ZF is added extra here. That's why what is the fault current expression? 3 times the V pre-fault by Z1 plus Z2 plus ZG0 plus 3 Zn plus 3 ZF. Okay, clear? And current relations will not change. That means IA0 equal to IA1 equal to IA2. So if you want the expression for that, simply V pre-fault by Z1, Z2, ZG0 plus 3 Zn. This is what? An extra 3 ZF. Clear? So that's about LG fault analysis. Now we'll move on to LL fault analysis. So let's see if there is an LL fault. We assume that the fault is in between B and C phases, okay, and the fault is not grounded since it is a LL fault. If that is the case, what is IA? 0. Boundary conditions I am writing because the before the fault system is not loaded, IA 0. IF equal to simply what? IB. IF equal to IB, that is nothing but minus IC, and VB equal to VC. So we can write sequence current relations. This is IA naught equal to 0, IA1 equal to minus IA2, and this is a sequence voltage relation. Okay. So IA naught 0 means you don't need to consider the zero sequence network. The zero sequence network need not be considered here. But for LG fault, yes, they have to consider because all the sequence currents exist. But here only what? Positive and negative sequence currents are exist. They are in equal magnitude and phase opposition. Phase displacement of 180 degrees because IA1 equal to minus IA2. And moreover, IA naught is 0. If you add IA naught, IA1, IA2, again you will get what? 0. No doubt, IA 0 na? Let's substitute. IA means IA naught plus IA1 plus IA2. Just look back. IA naught anyway 0. IA1 plus IA2 also equal to 0. Okay. And fault current expression, I am not going into the derivation. Directly I given IF equal to minus J root 3 IA1, otherwise plus J root 3 IA2. And the neutral current is what? IA plus IB plus IC. Just look back. IA anyway 0. IB equal to minus IC. So that's why what? IA plus IB plus IC 0. And even neutral voltage also 0 for LL fault. And LL fault, how many sequence networks are present? Only positive and negative sequence network. There is no concept of here zero sequence network because the zero sequence current during LL fault is 0. Clear? Now let's see what is the equivalent circuit here. Yeah, this is the pre-fault voltage and series with Z1 and IA1. This is the positive sequence and negative sequence, and VA1 equal to VA2 and IA1 equal to minus IA2. Proved with the help of circuit. That means using that VA1 equal to VA2, IA1 equal to minus IA2, I just realized the sequence networks connection for LL fault. Now this is a sequence network connection. So I can calculate IA1, that is equal to minus IA2. What is that? V pre-fault by Z1 plus Z2. This is a simple network. Voltage is there, Z1 and Z2 are in series. That's why voltage by total impedance will be IA1. That is equal to minus IA2. Now what is the fault current? Minus J root 3 times this IA1. Na? So minus J root 3 times IA1. Clear? Okay. Now for example, if there exists a fault impedance which is not equal to 0, then just go back. Yeah. If there is a fault impedance which is not equal to 0, na, then what happens? This is a VB and this is VC. So what I can write now? VB minus VC equal to IF into ZF if fault impedance is not equal to 0. Okay. So that is what I have written here. VB minus VC equal to IF into ZF. So if I solve this, then finally I will get VA1 equal to VA2. Sorry, VA1 minus VA2 equal to IA1 into ZF. Okay, how to realize that? Very simple. Have a look. This is VA1. Na? Here the potential is VA2. Na? VA1 minus VA2 is what? Here the current is what? IA1. Here the current is what? IA2. I told you just now. Due to fault impedance effect, current relations will remain same. Earlier, what is the current relation? IA1 equal to minus IA2. Now also. But voltage relations will change. Earlier, VA1 equal to VA2. But now, VA1 is not equal to VA2. VA1 minus VA2 equal to IA1 into ZF. So here VA1, here VA2. VA1 minus VA2 is the voltage drop across this. And that is what? IA1 into ZF. That means this equation is realized here. And finally, what I can say, the IA1 value and fault current. What is IA1? That is equal to minus IA2, V pre-fault by Z1 plus Z2 plus ZF. Only ZF is added here. But earlier if you see in LG fault, 3 times the ZF is added. Please careful about the difference. And fault current is minus J root 3 times V pre-fault by Z1 plus Z2 plus ZF. Okay. Now that's about LL fault analysis. Okay. So the first important thing is here the zero sequence current 0. And positive and negative sequence voltages are equal. Some of the sequence currents also equal to 0 because IA not 0, IA1 minus IA2, IA1 equal to minus IA2. That's why. Okay, clear. So that's about LL fault analysis. Clear. Now we will go for LLG fault. Again at the generator terminal, we assumed that there is an LLG fault. Okay, this is what the LLG fault. Since the fault is grounded here, VB and VC that equal to 0. VB equal to VC, but that is equal to 0. That I can say. And the IA 0 here, and fault current is nothing but what? Simple KCL, IB plus IC. Correct or not? That's the boundary conditions I written here. VB equal to VC equal to 0, and fault current is simply IB plus IC, and even IA also here 0. So, correct or not? Now what about sequence current relations? Very simple. IA0 plus IA1 plus IA2 equal to 0. Nothing great about here. Why? Because IA 0. IA means I can write IA0 plus IA1 plus IA2. So that's why IA0 plus IA1 plus IA2 equal to 0. And sequence voltage relations are what? VA0 equal to VA1 equal to VA2. That is equal to VA by 3. Okay, I'm not going into the derivation, but this is what? The sequence voltage relations. Since the 3 voltages are same, that's why 3 sequence networks are connected in parallel. Okay, so positive, negative and 0 sequence networks are connected in parallel for LLG fault, and fault current equal to simply 3 times the IA0. Okay, so this is the fault current, that is equal to what? Indirectly neutral current. Neutral current is what? 3 times the 0 sequence current. That is simple common sense. That's why fault current is nothing but the neutral current. Again I am saying here, fault current is nothing but what? Neutral current, or neutral current is nothing but the fault current, that is equal to 3 times the IA0. And there exists a neutral potential. What is the neutral potential? Again minus IN into Zn, otherwise minus IF into Zn. Clear? Now we will see the sequence networks here. Those 3 sequence networks are connected in parallel. So first using network reduction we can calculate IA1. For that these 2 impedances are connected in this, and this combinations are connected in parallel, that will be in series with Z1. And V pre-fault by the total impedance, if you look from here, will give you IA1. That I written here, V pre-fault by Z1 plus Z2 parallel combination with ZG0 plus 3Zn will give you IA1. Then after that you need to apply the current division rule. Means IA1 you know, opposite impedance. Why we take minus IA1? Because this is the incoming current, these 2 current must be outgoing. But what happening here? This current fundamentally incoming to the node. That's why minus we need to take. Minus IA1 into Z2, opposite impedance by total impedance, Z2 plus ZG0 plus 3Zn. And what is the expression for fault current? Simply 3 times the IA0. After calculating IA0, you can substitute here, we get the fault current for LLG fault. Okay, but if fault impedance not equal to 0, then what I get now? So VB equal to VC, but that is equal to what? IF into ZF. Okay, but if you really solve this, we get VA0 minus VA1 equal to 3 times IA0 into ZF, otherwise IA0 into 3ZF. So if you notice here, this voltage VA1, this voltage VA2. VA1 and VA2 are same, that's why this voltage you may say VA1 or what? VA2. Here voltage from here to what? Ground. Okay. Now similarly the voltage from here to ground is VA0. So this potential is nothing but VA0. VA0 minus VA1 is what? IA0 into 3ZF. That means 3ZF is what? Included here. That means we realized this equation using this simple 3ZF in the network. Okay. So now we can find out what is IA0, what is IA1 using what? Same rule. Okay. IA1 equal to what now? Very simple. The pre-fault voltage, IA1 equal to V pre-fault divided with Z1 plus Z2 parallel with ZG0 plus 3Zn plus 3ZF. Clear? That means just 3ZF is added here. Then after that, using current division, calculate IA0. Then after that, the fault current is what? 3 times the IA0. Earlier also 3 times IA0. Now also 3 times IA0. Okay? I hope you understand. Because due to fault impedance effect, voltage relations will change, but current relations will never change. Please notice that. So that's about LLG fault analysis. Now the last one is 3-phase fault. We already discussed triple L and triple LG fault analysis is same. This is a triple L fault, indirectly this is a triple LG fault. But whatever may be the fault, triple L or triple LG, VA, VB, VC equal to 0. And balanced currents, IA, IB, IC are what? Balanced. Fault current is nothing but you may say IA, IB or what IC. We can calculate the current flowing in each phase, and that is nothing but the fault current. But the magnitude of the currents are same. For example, IA is 10 kiloampere you got, IB is what? 10 at an angle minus 120 degrees kiloampere. IC 10 at an angle plus 120 degree kiloampere. If I ask fault current, simply you say 10 kiloampere. So that means IA is our fault current originally. So sequence current relation is that IA not 0, IA2 0, IA1 not equal to 0. Actually fault current equal to IA simply, that is equal to what now? IA1 only, because IA not IA1, IA not IA2 0. IA is nothing but IA naught plus IA1 plus IA2. IA naught 0, IA2 0, that's why only thing is IA1. And we get VA naught, VA1, VA2 0. Neutral current 0, because system is balanced and the neutral voltage also 0. And what is the equivalent circuit now? Only positive sequence network exists here. Why? Because since IA2 is 0. Okay, clear? So, and IA naught also 0, only positive sequence network, and that to VA1 0, that's why I represented with short circuit. Now I can calculate what is IA1 and what is fault current, V pre-fault by Z1. If ZF not equal to 0, then the ZF is added here. So what is IA1 now? V pre-fault by Z1 plus ZF, that is nothing but fault current. Now that's about three-phase fault analysis. Nothing great about the fault analysis. The simple thing is you need to careful with how the sequence networks are connected and what is the fault current expression. Okay, clear? Now if it is a loaded system, so how to calculate the fault current? See, if it is a loaded system, as we already discussed, that you must see pre-fault voltage first. Okay, let me draw the equivalent circuit here. See, this is the fault location. Before the fault, the generator is supplying the power to motor, and is clearly given the motor is drawing a power of P per unit at a power factor of PF at a terminal voltage of VT, that also in per unit, for example. Suppose if that is not given in per unit, actual values are given, let's convert everything onto common base first. For every problem, you have to convert everything onto common base. After converting everything onto common base, let's calculate VT in per unit, P in per unit, and power factor. That is not required to be in per unit. Power factor is 0.8 lagging, that's it. Okay, for example, it will not change whether it is in actual system or per unit system. Okay, so again I am saying first step is convert the entire network onto a common base. Second step is calculate where the load is connected, the terminal voltage will be definitely given, that load terminal voltage in per unit, load drawn active power in per unit, and then also then power factor, that is need not be in per unit, that's a simply factor, so that is as it is. Then after that, let's calculate the load current. How to calculate the load current? So P in per unit, even though it is a three-phase system, per unit is nothing but what? Magnitude of VT, magnitude of IL, and then what? Power factor. After calculating IL here, then you need to calculate IL. After calculating IL, the IL actual is equal to, IL phase are equal to magnitude of IL at an angle plus or minus cos inverse of power factor. If it is a lagging power factor, take minus sign. If it is a leading power factor, take plus sign. So after calculating the load current, the next step is, okay, so there are basically two methods to solve this. I am going to explain only one method, that is the Thevenin's theorem. So using Thevenin's theorem, what we need to do is here. So let's see, I am drawing the equivalent circuit. This is a generator. A voltage source in series with reactance, and after that transformer is represented with simple series reactance, and after that transmission line is represented with simple series reactance, and after that one more transformer, simple series reactance, and after that bus 4, and here the motor is located. Motor is represented with voltage source in series with reactance. This is the equivalent circuit, but where the fault is happened? Here. So this is the point we need to calculate V pre-fault. How? By using what? The terminal voltage here. Terminal voltage is given to you now in per unit, and you know the load current. The load current is what? Since we are converted all, all these elements onto a common base, and also what, in per unit. That's why in per unit, no matter if you have a transformer, the current flowing through the network is what, same. Correct or not? In per unit, primary current and secondary current are what, same. That's why. So let's see, this is what, JXT2, this is XTL, this is simply JXT1, transformer 1 reactance, this is JXG, now this is JXM. Clear? Understand? Now what is the next step is, let's calculate the pre-fault voltage. What is the pre-fault voltage here? Very simple. V pre-fault equal to terminal voltage plus JXT2 times the load current. So pre-fault voltage is ready. Now after that you have to calculate what is the Z Thevenin. How to calculate the Z Thevenin? See, you have to see from this terminal, by short circuiting the voltage sources, from this terminal what is the total impedance, that is Z Thevenin. What is Z Thevenin, sir? Z Thevenin equal to what? These three are in series, these two are in series, and the combination is in parallel. Let me write that, JXG plus JXT1 plus JXL having a parallel combined with JXT2 plus JXL. Once you are ready with Z Thevenin, then what is the fault current, sir? The fault current equal to simply V pre-fault by Z Thevenin, because that is by default three-phase fault, right? V pre-fault by Z Thevenin. So once you are calculated the pre-fault voltage by Z Thevenin, indirectly it is a subtransient fault current, and moreover you need to substitute here what? Subtransient reactances, generator and motor, because for a generator and motor subtransient reactance, transient and steady state reactance will be different, but transmission line and other elements, subtransient and transient and steady state reactance are same. Once you are ready with fault current, okay, if the question is simply calculate the fault current, okay, this is the answer, that's it, nothing else. But sometimes you will ask to calculate what is the fault current contributed by the generator and what is the current contributed by the motor current contribution and generator current contribution, he will ask you. In that case, what you need to do is this fault current must be divided into these two parts. Okay, see what is the generator contribution? Delta Ig double dash equal to, okay, If double dash multiplied with, okay, this current you are calculating, that's why what? Opposite impedance you need to multiply, that means XT2 plus XM divided with what? The total reactances, means what? XG, XT1, XT2 plus XTL plus XM. Using this you can calculate delta Ig double dash. Okay. Now what is the fault current contributed by the generator? Fault current contributed by the generator is delta Ig double dash plus IL. Load current you have to add. That's only different here. Okay. But what about the fault current contributed by the motor? See, first of all you need to calculate what is the fault current which is coming from this side. That is what delta Im double dash. How to calculate delta Im double dash? Simple, If double dash minus delta Ig double dash. Correct or not? So once you done this, then we can write delta Im double dash minus IL, because the load current you have to subtract for motor. Okay, clear? So that is how you need to calculate, right? If it is a loaded condition. Okay, clear? And the one more concept is fault calculations with DC offset current. Okay, there are simple formulas. I'm not going into that. You just go through the formulas. I'm not writing the formulas. Fault current with DC offset current. Okay, clear? So you just go through it. But now I will take up this last one, fault calculations using Z bus. Okay, for understanding, I'm just considering a simple example here. It's a 3-bus system. Okay, only at bus 1 generator is located. These are the transmission lines. So you know that for fault calculations, the shunt admittance of transmission lines are neglected. So that means every line having only some series reactance. Resistance also we neglect. Every line is represented something like this. X2, 3, okay. So using simple procedure you can calculate Y bus and Z bus. But careful, if you add the entries of first row, that will not be equal to 0. Why? Because there is an external reactance or external admittance is there. That's because of generator. So that's why simple logic is, if you add Y bus, if you add any row entries of Y bus, if that is equal to 0 means at that bus there is no generator. For example, first row not equal to 0, generator is connected. Second row, definitely you will get what? If you add equal to 0, 100% because no generator. Third row if you add also, we will get equal to 0. Clear? Because there is no generator at third bus also. Clear? So, and anyway, we can get Z bus also. After inversing Y bus, we can get Z bus. But anyway, in a given problem, Y bus and Z bus is given to you. And just take an example that the fault is at bus 3 with a fault impedance of ZF. Okay, if that is the case, the first step is the fault current. The fault current equal to the pre-fault voltages are generally assumed to be 1 per unit in this case. Okay, because before the fault system is not loaded, before the fault system is balanced, that's why internal voltage of the generator before the fault, e.g. 1 per unit, and all the bus voltages before the fault also 1 per unit, that you need to notice. And pre-fault voltage 1 per unit na, and that divided with Z33, that means you need to pick this. Z33 you have to pick plus what? ZF, that will give you fault current. After calculating the fault current, this is a one possible question, sir, calculate the fault current. That is very, very, very simple. Then second possible question is, what is the post-fault voltages at all the buses? Okay, how to calculate the post-fault voltages at all the buses? Very simple, have a look. To calculate the post-fault voltages at all the buses, the simple thing is, after calculating the fault current, the second thing is post-fault voltages at all the buses. Post-fault voltages at all the bus means, for example, V1 post-fault you need to calculate V1F. That is equal to V1 pre-fault plus delta V1. What is the delta V1 is? Very simple. Have a look. V1 of 0 is 1 per unit. What is delta V1? Delta V1 is nothing but the fault current minus of fault current multiplied with from the Z bus matrix Z13. Since we are calculating at bus 1, that's why 1 came here. Since the fault is happened at what? Bus 3. That's why Z13 you have to consider. Remember the formula. Okay? Clear? And you substitute, you will get this. Similarly, what about the post-fault voltage at bus 2? V1 of 0, pre-fault voltage minus, tell me, fault current multiplied with what? You are calculating for which bus? Second bus. Z2. Fault is happened at which bus? Third bus. Similarly, what about V3F? Sorry, this is V2 of 0. V3 of 0 minus fault current multiplied with, we are calculating for which bus? Third bus. Fault is happened at which bus? Third bus. That's it. You will get what? The post-fault voltages at all the buses. Okay, that is the second thing we need to calculate. The second possible question, what are the post-fault voltages at different buses? Okay, then the next step is, he will ask you that what are the currents flowing through different lines? Okay, that means what is the fault current flowing through line 1, line 2, line 3, something like that. Okay, I just given a direction, you can follow any direction you want. Okay, clear? For example, if you want to calculate the current flowing from bus 1 to bus 2, that means the line connected between bus 1 to bus 2. Okay, that is the third calculation. So you need to calculate the fault current flowing from the line connected between bus 1 to bus 2, for example. For that, what you need to do? I12 equal to the post fault voltage of bus 1 minus the post fault voltage of bus 2. We are already done now. Then that divided with what is the impedance of the line connected between 1 and 2. See how to calculate the impedance of the line connected between 1 and 2, not from Z bus, not from Z bus. This is from Y bus, from Y bus. How to calculate this from Y bus? Very simple. Let's go to the Y bus, pick the Y12, and minus it and inverse it. Minus 1 by Y12, simple, minus 1 by Y12. Similarly, what is the current flowing from bus 2 to bus 3? For example, 2 to 3, let's see, simple logic, V2F minus V3F divide with what? Z23. What is Z23, sir? Z23 equal to minus 1 by capital Y23. You pick Y23 and minus it and inverse it, we get Z23 and substitute, you will get it. And similarly, what is I13? I13 equal to, let me write here, I13 equal to V1F minus V3F post fault voltages by Z13. What is Z13? Which is calculated from Y bus. Let's pick the Y13 and minus it and inverse it. Clear? That's how we can calculate the current flowing through the any lines. Okay? Clear? That is the third calculations from using Y bus and Z bus approach. Okay? So, and the fourth calculation is that calculate the current contributed by the generators which is located at any bus. First of all, you need to identify on what buses the generators are located. For a given system, how to calculate? Very simple. For that, you need to approach the Y bus. Let's add the entries. Since anyway here the picture is given, if we add this which is not equal to 0, that means bus 1 having generator. If we add this, we got 0. So bus 2 not having generator. And if we add this, we got 0, for example. So bus 3 also not having generator. So that means where the generator is located? Only at bus 1. Okay. So that's why. So let's see the equivalent circuit. This is JXD. Clear? And this is what at bus 1 now? The post fault voltage of bus 1. And this is what? IG1. The current contributed by the generator at bus 1. This is what? EG, which is considered to be 1 per unit. Now let's see what is IG1. Very simple. IG1 is the fault current contributed by the generator at bus 1. That is equal to simply EG minus V1F divide with okay, JXD. Clear, sir? JXD. So JXD is given means you can directly do it. But if JXD is not given, then how to evaluate for JXD? Again from Y bus. JXD equal to, see, you need to add first row entries Y11 plus Y12 plus what? Y13. And inverse it. That will directly give you JXD value. That means impedance of the generator at what? Bus 1. Impedance of the generator at bus 1. This is nothing but what? Impedance of the generator at bus 1. That method will be used to calculate the fault current contributed by the generator. So these are the 4 calculations we will generally perform. Okay, clear? And one more, the miscellaneous point is here. For example, it is a loaded case. Loaded system. Loaded system means there exists a load current. For example, you have a generator feeding directly a load and the load current is known to you. Okay, but here the LG fault is happened. If there is a LG fault, what is the fault current IFLG? Very simple. 3 times V pre-fault by Z1 plus Z2 plus what? Z0. Z0 is ZG0 plus 3Zn. Okay, that's it. You don't need to consider the load impedance. But what is the fault current contributed by the generator? IFLG, simple, plus what? IL, nothing else, everything will same. Okay, but careful, sometimes he will ask you, what is the positive, negative and zero sequence components of fault current? See, positive sequence current component of fault current equal to negative sequence component of fault current equal to zero sequence component of fault current, that is equal to V pre-fault by Z1 plus Z2 plus what? Z0. Z0 means Zg0 plus 3Zn. Assume. See, this is what? Fault current. That means current flowing in the fault, positive sequence, negative sequence and zero sequence. But he will ask you, what is the positive sequence current contributed by the generator during LG fault? That is equal to whatever may be the positive sequence fault current. Come back. Whatever may be the positive sequence fault current plus load current. Clear? You must add the load current here. But what about the negative sequence current contributed by the generator? Nothing but the negative sequence fault current. Why? Because before the fault, system is loaded, fine, but balanced, na? That's why only positive sequence component of load current is there. Negative and zero sequence component of load current will not be there. That's what. And what about the zero sequence component of generator? Zero sequence current contributed by the generator equal to what? Simply zero sequence component of fault current, load current will not be there. That means the load current will be added only to what? Positive sequence, no matter what is the type of fault. Okay, clear? That is a one thing you must careful. This is, we are not covered actually in the lectures, but careful, sir. So if it is an LG fault, this is a method. Okay, LL fault means same, IA1 you need to add load current, IA2 you don't need to add load current. Okay, so careful about this, very simple trick, nothing else. Okay, so with this I am concluding fault analysis. Okay, so I am going to conduct a test tomorrow on this topic. Thank you.